All right, so we have explored the electrical resistivity of Earth materials, and there are some very useful properties of rocks with their electrical resistivity or conductivity dependent not so much on where that rock shows up on the geologic map, what color it has, but really on its current physical condition. How fractured is it? How weathered is it? And especially important is to electrical resistivity is what kind of fluid is in the rock and how much of it. How much is the porosity, and what is in that porosity in the rock. So this means that we actually have some geophysical techniques that are capable of examining those very um, those exact physical conditions, and this makes geophysical surveys of the electrical type um, useful for groundwater investigations, for pollution control investigations, um, for perhaps direct detection of oil or gas. Okay, so uh, we've implemented some of those resistivity techniques in the field, and this went pretty well this year in the Schurz area. But a year ago, for instance, it didn't go so well, and the reason was that, of course, to do an electrical resistivity measurement, you have to be able to put current into the ground, from these narrow little stakes that we have. We didn't have big pads to try to put current in over a very large area over very resistive material. So this year our stakes worked perfectly well in the relatively um, sort of normal alluvium that has some clay and some moisture in it and some salt um, for uh, um, for Nevada. But in the Lake Tahoe environment in the spring with melting snow, which is basically distilled water, um, and with no clay having weathered out of these very recent glacial sediments that we were trying to profile in last year, we basically struck out. We were unable to put any current into the ground, and thus we were unable to measure electrical resistivity in any meaningful way. So this brings up the question then, are there other ways of inducing and detecting currents in the ground um, than than by driving a stake into the ground and connecting or two stakes in the ground and connecting a battery across them and directly putting the current in the ground. And of course, there are many ways, and they do not. The special feature of electromagnetic surveying methods, which is what we're going to talk about, is that they do not require that we use direct ground contact. Okay. Now, when we talk a bit later about the magnetotelluric method, we that method really brings together measuring currents in the ground through direct electrode dipoles, also measuring the magnetic field and measuring the electric field. So there are ways of bringing that all together, and they're especially used by academics for very deep probing, say, of the upper mantle and lower crust. But for engineering purposes, for purposes of fault detection or for water resources, energy resources, um, pollution control purposes, these electromagnetic techniques are very very useful, and they're especially useful for those environments where it is extremely difficult to put a current in the ground. So we're going to take advantage uh, of the frequency of electromagnetic waves. Remember, our even though our mini res ground resistivity unit has an actual operating frequency of 5 hertz. That's only to avoid setting up a too much battery effect, too much movement of ions in the ground. Okay, and it's an essentially direct current technique. Now, direct current means the current is the same, certainly flowing in the same direction all the time. What comes out of a battery. But of course, what you have in your house is alternating current, AC. Okay, and the current is actually at least supposed to be a sine wave, and that current is alternating between flowing one direction and flowing another. And at the 60 hertz AC frequency that we have in the United States and in Europe, it's reversing direction 60 times a second. Okay, which is not that not that fast, but maybe we should pause and think about what we can do with these waves that are alternating currents of uh, alternating currents and have different frequencies. So we need to consider the electromagnetic spectrum, which I'm giving you here the geophysical electromagnetic spectrum. So we have low frequencies on the left, and for instance, the red frequency that's most on the left, 10 to the minus 1, zero point 0.1 hertz. Okay, that's a cycle every tenth of a second, which means that the period of the cycles in time is 10 seconds. Right, here's 10 hertz. Right, 10 to the second hertz, that's 100 hertz. 10 to the fourth, 10,000. 10 to the sixth, that's a million hertz or megahertz. Right, 10 to the eighth, 10 to the 10th, and right in the middle would be 10 to the ninth, a billion hertz. That's a gigahertz. Right. Um, so there are some things that our society uses these frequencies for very commonly, and the uh, and so for your reference, okay, um, the of course direct current DC is infinitely far. It's at exactly 0 hertz, which on this log scale is infinitely far to the left. But effectively just off the left side of the scale. Okay, um, we don't care whether it's we tend not to be able to distinguish whether it's 100-second point 0.01 hertz frequency or direct current. We might call it direct current. Um, then in bold, well, okay, so let's see some common technologies. Okay, so alternating current AC power in the U.S. At 60 hertz, so that's about here on the scale. All right, and AM radio, okay, is in effectively megahertz. All right, it's right about 1 megahertz. Um, and then FM radio is at hundreds of megahertz, below gigahertz, but VHF is at um, just less than 100 megahertz up to a few several hundred megahertz. Okay, and then when you get up to a gigahertz, the TV band essentially ends. There's some overlap, and what you have are TV companies selling off that overlapping frequency to cell phone companies, because cellular phones start at about a gigahertz and go up to a few gigahertz, not 10 gigahertz, but a few gigahertz, 10 to the ninth hertz, um, and uh, and there's all common things like Wi-Fi that also operate in the gigahertz range. Okay, we'll hear more about GPS, which is operated um, in the gigahertz range. Okay, Of course, cell phones communicate by radio waves, and they represent cell phones, and Wi-Fi represent the upper end of the radio wave frequencies. At the lower end, these arrows go on for a ways here, is super low frequency radio. Um, I think ham radio, all that is up in the toward the FM band, somewhere within the TV band. But there are radio waves used to communicate with submarines that may be 1 kilometer below the surface of the very conductive ocean water, and those are basically operating at very close to 60 hertz, maybe even only 10 hertz. So on your gigahertz Wi-Fi network, you can get gigabit transmission of data, but on your 60 hertz, submarine nuclear launch code type of communication, you get maybe 10 bits per second. Okay, and if you're talking about nuclear launches, that's okay. You want it to be slow, and you want the message to be very sure. Okay, so radio waves essentially cover most of this electromagnetic spectrum. Now, I want you to notice the scale at the top. Okay, so at the top, we've taken the frequency, and let's see, remember that V equals F lambda. That's true of light as well as for sound waves, and it's true of radio waves and everything else. Okay, so if you want to get lambda, the wavelength, okay, you just take the velocity, which is the speed of light. The speed of light in vacuum is basically the same as the speed of light in air. Not exactly as the GPS people will tell you, but pretty close. And you divide it by the frequency. Okay, so at a frequency of a megahertz, okay, for those AM radio waves, the wavelength is 300 meters. For the 10 to the ninth, okay, at a gigahertz, the wavelength is at about I suspect that's going to be 30 centimeters. Okay, 0.3 meters. All right. The FM radio band is at about 3 meters wavelength. Okay. And down here, you go down to 30 kilometers or up to 30 kilometers wavelength at 10,000 hertz. All right, up to let's see, it would be 3,000 kilometers wavelength at the frequency of AC power. Okay, so we're getting pretty long wavelengths for those low frequency waves. So okay, what are the geophysical uses of this? Now, one of a very early and very very simple kind of electromagnetic geophysical instrument is the metal detector. Okay, and it's operating over frequencies of maybe 1,000 hertz to 10,000 hertz. Now, if you have ever used a metal detector, you know that it has found something when it squeals at you. Okay, and we'll get to exactly what's happening there, but you can actually hear the frequencies that it's using to put waves, electromagnetic waves, into the ground. Okay, so the metal detector is, and that's you use it with earphones to hear that squeal, and that's when you know when you've located something. Okay, so the metal detector is operating over, being operating over 1,000 hertz, a kilohertz, 10 kilohertz. Well, that's actually the same range as you hear. And so even though it has nothing to do with sound waves, okay, really, the metal detector is one of the so-called audio um, uh, electromagnetic instruments. It's an audio frequency electromagnetic instrument. Okay, it's let's see, the A4 A on the relatively low on the piano keyboard is 440 hertz. Okay, so that's up here, well within the audio range. All right, and these audio frequencies that these instruments are using are just a little bit higher than that, up to 10,000 hertz. I'm sure that I can't hear anything over 10,000 hertz in frequency. Probably you guys can. You're younger than I am. You probably hear up to 20,000 hertz, which is up to about here on the scale. All right. So the metal detector, audio frequency. There, I'll talk briefly about magnetotellurics, which is a essentially low frequency, deep probing way of looking at electromagnetic fields. Okay, so that really starts at about in the audio range, but goes down to extremely low frequencies. And we'll see later when I talk about skin death why you have to go to such low frequencies, 10 to the minus 4 hertz, which is essentially 10,000 seconds period. Okay. Let's see, 3,600 seconds is an hour, so that's like 3 hours period to the waves. Okay, which is very similar to the not that far off the diurnal variation of the Earth's magnetic field. Aha! Well, there is a connection there. Okay, and I'll talk about that slightly. All right, induced polarization, goes down to DC. Right, we used our DC instrument to look at uh, the uh, the complex component of the resistance. Okay, and that's really looking at the induced polarization effect, which really doesn't occur above about 10 hertz. All right, 10 cycles per second, and this big red arrow here is meant to say, okay, it goes all the way down to 0 hertz, which is off this log scale. All right, at the high end, okay, we have ground probing radar (GPR), okay, which is up in the hundreds of megahertz, gigahertz range, and then we have in the middle, in the audio range, there are these audio magnetotelluric instruments, audio um, uh, um, audio electromagnetic instruments. Okay, and they're using frequencies of waves that are in that audio range. A few hundred hertz up to 10 kilohertz. Okay. Now, what about the names of these instruments? There's the EM31, which is what we used. I think it was the 19 might have been the 1992 class to to profile across the Pahrump Valley Fault, and we found shallow conductivity anomalies. It was with an EM31. Okay, and that's a very nice conductivity electromagnetic instrument. It's at least as simple to operate as our mini res, and as you know, that's really saying something. Okay, then down at lower frequency is the EM34, and I'll show you pictures of both of these. These are both frequency domain instruments, electromagnetic instruments. Okay, so just like all these different technologies, right now we're society's exploiting very well the gigahertz range, but we're extremely reliant on the 60 hertz range as well. Um, just like society has uses for all parts of the spectrum, so do geophysicists. Now, why are we talking um, about frequency of electromagnetic waves? Okay, um, why are we um, why are we um, concerned about what the frequency is, and why are there so many different geophysical instruments that are looking at the different the different parts of the frequency ranges? Okay, um, and it really boils down to this effect called skin depth, which is this small Greek letter delta. Right? It's not a capital delta uh, like you've seen before. That's a small Greek delta. Okay. Now, the problem that we have as geophysicists is that our rocks are generally pretty conductive. Okay, I mean we can take radio waves of any frequency from 10 to the minus 4 hertz all the way up to 10 to the 10th hertz, 10 gigahertz. Right? We can take any frequency of radio waves and we can broadcast that through the vacuum of free space, and it not much will happen to that. I mean, it disperses according to spherical divergence, right? Just like sound waves, just like the waves from our hammer hitting the plate. Okay, right. The farther away you are, the lower the amplitude. But there isn't, radio waves can persist through incredible different distances, right? We can get radio signals from quasars that are billions, more than 10 billion light years away. Okay, uh, most of the way across the universe, we can get a radio wave. All right, so we can use any. We should be able to use any frequency we want, right? And why not use for we have the same resolution issues that we do with seismic waves, right? The higher the frequency, the better the resolution will be, the better our pictures. Okay. Yeah, but here's the trouble. Okay, we're not propagating our waves through free space. We're propagating our waves through conductive ground. Okay, and whenever we have any conductivity in a material, it's going to absorb those waves. Okay, and that's why you can't get a cell phone signal in the basement of this building, right? Because there's just too much metal, too much concrete, too much soil between your cell phone and um, the cell tower. All right. So, however, you know, even hitting the surface of a metal plate, a radio wave doesn't, instantly and immediately drop to zero in amplitude. Okay. There's some depth to which you still will be able to detect the that signal. Okay, so skin depth is defined in an exponential way. It turns out that the wave amplitude, the radio wave amplitude, dies exponentially as it gets below the skin the 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 surface of the material. Okay, and we can examine for different experiments for different materials. We can examine what the skin depth would be. Okay, so skin depth is defined as the depth below the surface, with the air or the vacuum, effectively, um, at which the electric amplitude is decreased to 37% of what it was right at the surface. Okay, it's basically 1/e of the original amplitude. 1/e is 0.37, which is about 37%. Um, and so we have skin depth being minus alpha z, which is well, e to the minus alpha z is equal to e to the minus 1. And so at z equals 1 over alpha, we have our skin depth. Okay. Now, what material properties determine skin depth? All right. So delta here, all right, is equal to the square root of 2 divided by the angular frequency of the wave, omega. That's a small Greek omega. Okay, divided by the magnetic permittivity of free space. I think that is, and then divided by the that's a small Greek sigma, which is this is, let's see, we had omega, mu, and sigma, and the sigma is the which I hope you recognize by now, is the conductivity. Okay, so let's put this into some terms that we're a little more familiar with. Okay, so omega is just 2 pi f, right? The frequency in hertz. You multiply that by 2 pi, you get the angular frequency in terms of radians. Okay, so 2 pi f, and the magnetic permittivity is 4 pi times 10 to the power of minus 7. Okay, it's a small number, and then the inverse of sigma is our familiar rho, our resistivity property of rocks. Okay, so we have 2 rho divided by 2 pi f divided by 4 pi times 10 to the minus 7. All right. So if you take these constants here, the 2 pi, the 4 pi, the 10 to the minus 7, and you invert them, and you take the square root of that, you get about 500. Okay, where rho is in. I'm sorry, the skin depth delta is going to be in meters. The resistivity is in ohm meters, and the frequency f is in hertz. Right, you get about 500 times the square root of the resistivity rho divided by the frequency f. Okay, now this has some pretty spectacular implications right away, right? So how do you get a big skin depth, right? If you want to see down, right? If you want to be able to measure that signal in the ground, okay, or see conductors that are down, below the surface of the ground, okay. There's 2 ways you can do that. You can have a very resistive, right? If the higher the resistivity, the larger the skin depth, right? You can have a very resistive ground, or if you're stuck with the ground you're stuck with, then what you want is a very low frequency, right? The higher the frequency is in the denominator. So the higher the frequency, the smaller the skin depth, right? So the skin depth is not just a function of the ground; it's a function of your whole experiment, because your whole experiment is going to tell you is going to tell you how your whole experiment is going to tell you what your frequency is that you're using. So, for instance, with a with a DC direct current resistivity experiment, right? Driving stakes into the ground and putting currents into the ground, we're effectively using 0 frequency, right? So you take rho and you divide by 0. Well, okay, effectively, it's infinite, right? So that's why resistivity is used to look very deep. But the trouble is, of course, that then you have to have big, long wires, and you got to have huge generators and gigantic high voltages that can kill people. There is other factors than skin depth that limit resistivity. But resistivity is an attempt to get around the skin depth by using 0 frequency, right? So very low frequencies then are going to have larger skin depths. Okay, so if we go back to the electromagnetic spectrum, what we see right away is that the techniques we use to sound the deepest are the ones that are on the left, and the techniques that we use to sound just in the very shallowest areas, okay, those are on the right. Okay, so notice that you know our frequency domain sounding techniques, EM34, EM31, metal detectors, right? Using those audio frequencies, they have very long wavelengths, right? And that that allows us to look deep into the well, into sort of engineering depths. Maybe even up to 100 meters depth. We want to look, to thousands of meters depth. We got to use magnetotellurics. Okay, ground probing radar with a frequency, a much higher frequency, by 4 orders of magnitude, and a wavelength of only 3 meters. Well, GPR will see we'll see a few meters into the ground. Okay, and we'll see the advantages of GPR and what we can get in those upper few meters. But the skin depth is effectively going to limit GPR because of its high frequency. Okay, so it's well worth trying to memorize this, at least this skin depth approximation, right? 500 times the square root of rho over f. All right, because that tells you a lot about what your electromagnetic technique is going to get you. Okay, so here's just an illustration of the skin depth. Okay, high frequency waves die out faster, low frequency waves die out more slowly, and they see a bit deeper. Okay, actually not that different from REMI. Okay, and surface seismic waves. Okay, here's an illustration of inducing a current on the surface of the ground. Maybe that current's induced by radio waves, and that current is going to die out exponentially, actually, with depth. Okay. So how do we how do we then get some information? We're not going to put direct current directly into the ground. We want to put current somewhere else and be able to cause currents in the ground. And so the whole electromagnetic geophysics enterprise is based on essentially on this Faraday's law. Okay, so if you have some number of turns in a coil, okay, which is an inductor, all right, and you have a magnetic moment, which is a magnetic field strength times the area of the cross-sectional area of a coil. All right. Now, if there's some change in that magnetic moment, okay, if the strength of the, you can change the area certainly, although in the field that's kind of hard to do, but that would be one way to do it. But if the magnetic field itself is changing, okay, that the strength of the field is changing B, and of course the Earth's magnetic field changes very slowly over about a 12-hour period. So we could think about getting that very very long wavelength 10 to the minus 3 hertz waves just out of those diurnal changes in the Earth's magnetic field due to the sun warming up the ionosphere, right? Good think about that. But maybe we'll put in a magnetic field that changes. Okay, if you take that change in the magnetic field in the magnetic moment, and you divide by a change in time, right? So wave motion is pretty typical, right? There's always a change in magnetic moment. The wave is changing. And if it's an electromagnetic wave, then the field strength can be changing, even if we hold the area constant of our coil. Okay, and it's going to change over some period of time, right? So we put a sine wave in, right, and we'll see these changes. and we could put a additional turns on in the coil. That's each turn has the same area, right? And then that'll reinforce. Okay, what do we get? Right, the larger the change. Okay, and the smaller the time that it takes to change in. Okay, and the more turns we have in our coil, right, we're gonna get more voltage. All right, so all of this, changing magnetic field, um, changing over different times, that generates voltages. Okay, in the coil. All right, that's Faraday's law essentially. Written in practical terms. How do you measure it? All right, so here's some illustrations. Right, got Faraday's law at the upper left. All right, so we have a coil of wire. Right, so here's 2 turns of wire, and we hold a magnet near the wire. Okay, and I probably should do this experiment. In front of you using an actual magnet and an actual voltmeter, right? And if there's if I hold the magnet still and the coil still, then there's no change in the magnetic field. Okay, and so the current that's induced in this wire is nothing, and the voltages are nothing. Okay, there's no change, right? So according to Faraday's law, there's no voltage generated. As soon as I move that magnet relative to the coil, okay, then that's when we get a voltage. And to get a voltage, you got to have a current. So, and of course, this is the principle that that electrical generators work. The ones in Hoover Dam to the ones in your Honda generator. All right, so that's Faraday's law, in action in your house. All right, so we have to have moving magnetic fields, changing magnetic fields. And here we change it by moving the magnet around relative to the coil. Okay. Now we have a different direction of change, and we'll get a different, we'll get the negative of the voltage. Okay. So this acts in Faraday's law is one of those fundamental laws of electromagnetics. Okay. But when we're dealing with materials that have finite resistivity, finite conductivity, okay, there's this effect called Lenz's law that that occurs, okay, and this is what we're going to use to our good effect, okay. Now I'm kind of getting ahead of the game here by showing you this picture, but basically, when there is that EMF, that voltage generated by a change in magnetic flux, okay, according to Faraday's law, all right, there will be an induced electromagnetic flux, EMF, an induced voltage, and that's going to produce a current whose magnetic field opposes the change which produces it. Okay, now you can see this in inductors. Inductors act to delay and change the phase of the waves that are in the wires that go into the inductors, and the Earth does the same thing, and we're going to take advantage of that. Okay, the conductive Earth basically is a giant inductor of a kind, and when we change a magnetic field, okay, and so we can set up a transmitter and we can put a sine wave of current through that, okay, alternating current through that, and so the magnetic field that's being generated by that transmitter loop is going to be constantly changing. and it's going to, every time there's a change, it's going to induce a counteracting eddy current. Okay, and that counteracting eddy current is going to give us a counteracting magnetic field. Okay, so the inductor, is resisting the changes in the magnetic field, right? If we change the magnetic field, um, shake a bar magnet up and down, then the low frequency radio waves, are going to go up into free space and out of the atmosphere, and all the way out to infinity. Okay, all the way out to the edge of the universe. Um, but uh, they're not going to go very far into the ground. Okay, at least in any detectable signal. And really, the main reason for that is because, according to Lenz's law, the ground is going to set up currents in it that are going to resist the changes in the magnetic field. Okay, so it's Lenz's law that we take advantage of to, essentially find a way of putting currents into the ground and detecting those objects, those conductive objects remotely. Okay, to change the magnetic field in the ground, we don't have to touch the ground. Okay, we could fly over it and induce magnetic fields without having any ground contact at all. Now, these eddy currents, the the inductance principles, okay, they come from the basic laws of electromagnetics, um, and so part of those are Ampere's and the Biot-Savart's laws, okay, and so how does a current induce a magnetic field? Okay, so we have now a we have a piece of wire here, which doesn't have to be straight, and along that piece of wire we have a small element, and there's a current I, with I amps that is flowing in that piece of wire. Okay, and so across this little element, little just very tiny dl long. Okay, the current is flowing in this direction. Okay, so I is an amount of current, and dl is a very small length, but that length has a direction. So dl is a vector. Okay, so there's the vector dl. Okay, and there's a current flowing in there, and so the question that this asks us is, what is the magnetic field, or the change in the magnetic field, produced by that current? Okay. No, I'm sorry. What is the magnetic field produced by that current? All right. So because that flowing current is going to produce a magnetic field, and if it's a constantly flowing current, it'll produce a constant magnetic field. Okay. And also, this equation works both ways. Okay. A magnetic field will produce a current. Okay. At least a changing magnetic field. All right. So now we need to use another vector, and this vector is called the vector 1 sub r. Okay, and that's a unit vector. Okay, the 1 vector is a unit vector in the direction between where we're trying to observe the magnetic field and that little current element. All right. So what you do is you take that little current element vector and you take the vector cross product with the against the 1r vector. Okay. So here, you would dot or cross L with R, or L with 1, right? So then the cross product, according to the right hand rule, is going to be pointing into the screen here. Okay, and that's what it's not showing so well, but that's what'll happen. And then that gets scaled by the current, right? The larger the current, the larger the change in the magnetic field. Then there's the magnetic permittivity of free space, mu0, and then divided by 4 divided by pi divided by the distance r squared. Okay, and that gives us, so magnetic fields also fall off by r squared, right? Just like gravity. This is how magnetic fields are a potential field. Okay, so that's the relationship between current and magnetic field. All right. So then, according to Ampere's law, right? If we have a current that's twisting around the loops of this coil, okay, twisting around the loops of the coil, right? This current I, then we're going to get straight lines of a magnetic field. Okay, it's the same cross product operating there. Okay, and here is a standard inductor, a coil operating in in a free space. It's going to be generating these magnetic lines of force, which, since there is no such thing as a magnetic monopole, come around back to the other side of the coil, even if they have to go, to the other side of the world to do that. Okay, so Ampere's law. All right, so we have to put in some kind of change to a magnetic field into the Earth, and then we'll get eddy currents. We'll get resistance to the changing magnetic field. We'll get Ampere's effects, and those are going to allow us to get some measurement of the conductivity of the material in the ground, the resistivity of the material in the ground. So there are two approaches. Okay, there's frequency domain magnetic EM surveying and time domain EM surveying. Okay, in the frequency domain method, we have a transmitter coil, which is going to put in we put a sinusoidal alternating current through that coil, and so that coil is going to produce a sinusoidally alternating magnetic field. Okay, and then a little ways away we'll have a receiver coil. Okay, which of course is going to see. I mean, it's just nanoseconds. Hundreds of picoseconds. Over for the speed of light to get from our transmitter to our receiver coil. Okay, so the receiver coil will see exactly the same exactly the same transmitted magnetic field. So the receiver coil will see that, but it will also see something else. It'll see an induced magnetic field, which will be delayed by a whole lot more than nanoseconds. Okay, and in fact, we'll be able to tell that it's delayed by a certain phase, a certain like percentage of the 360 degrees angle rotating around the circle that are from peak to peak. Okay, so here this phase difference would be looks like 1/7 or 1/6 of the so it would be 60 degrees out of phase. Okay, and that's due to this changing magnetic field, this sinusoidally changing magnetic field, inducing sinusoidally changing eddy currents. Okay, within the ground. All right, according to Lenz's law. The other thing is we can have a transmitter current, and so we set up a constant magnetic field which is extending into the ground, and then suddenly we shut it off. Okay, and we go maybe another fifth of a second or maybe a couple of seconds, and we ramp up the current in the transmitter again. It is possible to cut off a current very, very fast, but it's harder to instantly start a current. Okay, in our coil, in our transmitter coil. So we got to ramp it up. All right, and then we cut it off. And we go in opposite directions because we want to avoid battery effects and just measure um, that fundamental resistivity property, right? That fundamental conductivity property that's the same, whether it goes one way or the other. All right, and so we'll get, the cutoff of the currents is the thing that has the largest or the smallest delta t. Okay, and so that's going to produce the largest induced voltage, induced EMF, electromotive force. Okay, induced EMF, induced voltage. Right. So the cutoffs are going to produce these big voltages. Okay. Now, however we do it, in the frequency domain or the time domain, all right, we are basically going to have a transmitter loop, a coil, transmitter coil, and a receiver coil. And the transmitter is going to induce a primary magnetic field. And so here's some magnetic lines of force for you. And then down into the ground, we're kind of looking obliquely down into the ground. There's this conductor, maybe a piece of a dike that's mineralized and is more conductive, or maybe a piece of a fault zone that has saline water in it, so it's more conductive. Okay, so that the magnetic field is going to cut across or cut along the conductor. Okay, if it cuts along the conductor and we shut it off, then suddenly there's going to be these eddy currents. Okay, that are going to be resisting that shut off. Right, so those eddy currents are going to be looping around the this is an attempt at a 3D diagram here. Those eddy currents are going to be looping around those changing magnetic fields. Okay, and those eddy currents themselves, but you notice that the eddy currents are constrained. They can't go exactly where they want. Okay, because there's this limited conductor. Okay, and that's exactly what we want to find, because the eddy currents themselves will also generate a secondary magnetic field. And so not only do we pick up the primary magnetic field in the receiver, okay, but the eddy currents are also going to be picked up. The eddy currents are producing a secondary magnetic field. It might be a lot weaker, right? But it's also going to get picked up by the receiver. Okay, and so that's really where we get our ability to cause currents in the ground and then measure them. Okay, and the strength of the eddy currents, right? The strength of what our receiver sees, that's not exactly the same as the transmitter current, right? That strength is really what that strength is going to be proportional to the conductivity of the of this structure, whatever it is. Okay, now we got to think about how do we induce eddy currents the best? Okay, so here's this is actually a model here, an inside view of the EM31. Okay, and it's got a transmitter loop on the left and a receiver loop on the right, and the center of the transmitter loop is 3.67 meters from the center of the receiver loop. Okay, it's kind of an awkward thing to carry around, but you don't have to stop and pound in stakes everywhere. Okay, so you just walk around and try to get thrown off balance by this 3.67 meter long pole that you're carrying around horizontally. Okay, so this is a cross section. We're looking into the ground down here. We're carrying the transmitter receiver pair above it, and we're making a traverse. We'll start on the left side and we'll traverse over to the right. Okay, and then this is a coin-shaped conductor that we're looking at the edge of, right? So the conductor extends, into the screen and out of the screen, but you can see it does it. It's oriented perpendicular to the traverse direction. Okay, so here we're putting changing magnetic fields through that conductor, and we're getting those eddy currents because the magnetic fields are constantly changing. They're sinusoidal in the EM31. Okay, and so those eddy currents are setting up their own magnetic fields, right? They can't have exactly um, they can't take exactly the shape they would like to take in the ground because they're restricted to the conductor more or less. All right, and so then we'll try to see the magnetic fields generated by the eddy currents in the conductor. We'll try to see those with the receiver loop. Okay, so let's say we have a transmitter and receiver. Okay, and we're at position 1, which is the most to the left. Okay, and the transmitter is inducing an eddy current in the vertically oriented conductor, and that's producing its own magnetic field. But notice what happens here: the magnetic field coming, when the receiver is right above the conductor, the magnetic field that's cutting through the receiver coil is horizontal. Okay, it's horizontal lines of magnetic force. Okay, and our receiver coil is also horizontally oriented. So there's no lines of force that are cutting, through, down within the loop. Okay, and so it doesn't cause the receiver any voltage, right? So there's no coil anomaly on the horizontal coil. Of course, you reorient the coil to vertical, okay, and you would see an anomaly over the conductor. All right, so then we move on, and the conductor is in between the transmitter and the receiver. Okay, and in this case, the secondary magnetic field is resisting the changes in the primary field. So they're going to oppose each other, and so our receiver is going to see a total magnetic field that is less than it was if the conductor was not there. And then we get the transmitter directly over the conductor, and here the transmitter lines of magnetic force are going right along that conductive dike, okay, and so they're not inducing any eddy currents, right? They have to be cutting across the dike, right? In electromagnetics, kind of as in magnetics, okay, all these vector things are really important, and so directions matter, whether the transmitter and receiver are horizontal or vertical, right? So the transmitter is putting out lines of force that are going right along the conductor, no eddy currents. Okay, so the receiver is not measuring anything at all. So position 1, we're measuring 0. There's a position 3, we're also measuring 0. Position 2, we have a minimum. Okay, most resistance to the signal, and that's what you'll see in the receiver coil. And this is exactly the the technique we use to look at faults with the audio frequency EM31. It's exactly what we use to look in Pahrump Valley at the conductive fault. Okay. Now, if you just are surveying over an area that's flat, okay, you're not going to generate eddy currents, and you will. Well, the eddy currents are going to be kind of proportional to the conductivity, and so you can get your measurement of conductivity. Of course, if you have places where maybe there's a change in depth, right? Then you can start getting some more prominent measurements, and you can do 3D profiling with this. Here's a horizontal transmitter coil and a mobile receiver coil, and there's a conductor there. It's going to be its magnetic field is constrained to it, and so you can basically go around and measure the eddy currents, and where the the eddy currents are the strongest, the magnetic field from the eddy currents is strongest, you're getting nearer to the conductor, even though your transmitter is fixed. Um, and you need an EM31 can't do that kind of fixed loop and mobile receiver, but there are other instruments that can. All right. Now that's about frequency domain electromagnetic surveying. What about time domain? Okay. In time domain electromagnetic surveying, you you have that transmitter current that shuts off suddenly, and the induced voltage in the ground, due to the eddy current, is going to be in the opposing direction. It's going to oppose the change. Okay, and then you start up the magnetic field in the opposite direction. You shut it off suddenly, and you're going to have this induced voltage that's opposing the change. Okay. The secondary magnetic field, due to that, due to those current cutoffs. Okay. I mean there is a small induced voltage when you're ramping up the current to start it again, but that's too small to observe usually. So let's just let's look at what happens due to the induced voltages. Okay, and that secondary magnetic field after the cutoff, right? It's opposing. Okay. And it's from the eddy currents, and suddenly it was noticed. I don't know by who actually. Okay, that secondary magnetic field from those induced currents, it doesn't die off immediately or with the speed of light. It dies off much more gradually than that. It dies off over like a second. Even though the eddy currents are only at maybe 100 meters depth, it takes a second to die off entirely. And it turns out that the faster it dies off, the higher the higher the resistivity. Okay. So now we can look at in the time domain, we can look at how fast these secondary currents die off, and that's going to tell us something about the resistivity. Okay, time domain electromagnetic measurements. All right. It turns out that if we put a horizontal transmitter loop, in other words, with a vertical vector moment, okay. So we have this transmitter loop lying on the ground, circular or square or whatever it has to be. Okay. And we shut off the current in that transmitter loop. Then we get an eddy current, okay, which is going to start right under the transmitter loop in that instant after the cutoff, nanoseconds after the cutoff. But if you look several milliseconds later, that eddy current is going to sink into the ground, and it's going to open up in size, kind of like a smoke ring. All right, and it's becoming more ephemeral, and by the time you get to time 4, the eddy current is not nearly as strong, but it's gone down in depth, and also opened up to a larger area. Okay, aside from just being weaker. So looking at different times and how the strength, all of these eddy currents at all these different times, they're producing this instantaneous magnetic field that we can measure with a receiver loop. Okay, and the that sinking eddy current, we can tell, we can maybe make measurements of how fast it's sinking in the near the surface, and how fast it's sinking at some greater depth. And it turns out the rate of sinking of that eddy current, okay, is proportional to Earth resistivity. amazingly enough. Okay, and this is in a this kind of eddy current can appear in a constant velocity medium. We don't need a near planar conductive object. I'm sorry, in a constant resistivity medium. Okay, we don't need that dike-like conductive structure. So back to Lenz's law. Okay, we have a transmitter loop, and here is a snapshot of the eddy current at the time when it's at this depth. Okay, the eddy current begins right under the transmitter loop. At the instant, a nanosecond after it's shut off, and after 10 or 50 milliseconds, it's only propagated maybe 150 to 100 meters in the ground. Okay, and we might be able to track it down to a whole second when it's sunk maybe a few hundred meters into the ground. All right. So we have this kind of magical smoke ring eddy current that we got just by suddenly snapping off a transmitter loop that had a current in it until we shut it off. Okay. So that's that's the basics of time domain electromagnetic surveying. Okay, let's look at some of the instruments. There's such a variety of instruments. This is a L&R Instruments Mini EM, which I think would be well worth finding and getting one. So it's a 2-meter long frequency domain EM device, and it's got coils at both horizontal and vertical orientations. Here's a Geonix EM34. Okay, and this device has 2 coils and 2 boxes, and you got to link the boxes with a cable, a signal cable. Okay, and so you can separate the coils by as much as you want. You can at least as much as you have wire for, and you can put the coils in any orientation. Here is a where both the transmitter and the receiver are in a vertical and inline orientation. You could have a vertical transverse orientation. You could have a horizontal orientation, and you could have a different orientation for the transmitter versus the receiver. Okay, and also there's different distances. So here you can set up kind of a seismic-like experiment where you open up the distance. And you take all kinds of different measurements at each distance. And of course, you're opening up in distance around some center point. Okay, or you might actually decide you want a like a constant A spacing. You want a constant distance, and you're just going to move down the line like that. Okay, all time honored. Here's a photo of an EM31, a Geonix EM31. All analog. You get it reads conductivity out of a dial on the top. Incredibly simple. Okay, but cumbersome to carry around, but not that hard to carry around. Okay, lots of measurements made very easily. Okay, time domain instruments. Those were all frequency domain instruments. Okay, time domain instruments are much more difficult to construct and much more difficult to interpret the data from. Okay, I would agree that the premier time domain instruments come from Zong, headquartered in Tucson, Arizona, with an office here run by a Mackey alum in Sparks. Okay, and the nanotem means that it's sensitive to time domain electromagnetic measurements, and the nano is suggesting what kind of currents it's sensitive to. Okay, so you have a great big transmitter loop for a huge magnetic moment. Big area, large magnetic moment, and you put a big current through there, big current I. And then the transmitter box has the ability to shut that off very quickly. Okay. Then you have you want a very sensitive receiver loop, so that tends to be thousands of turns of wire around a very fine wire around a a circle that's maybe the circle might be um, 1 meter in diameter. Okay, and then basically connected to a voltmeter that's able to collect much like a seismograph that's able to collect the data at these milliseconds of time after the transmitter loop is shut off. Here's the Geonics Pro 10. Um, a very respectable instrument, but not as flexible and maybe not quite as difficult to use as the Zong, which is really the premier instrument. Okay, so those are some of the instrumentation that's available or been available lately. Okay, all right. So I will go on in the next lecture to talk about some more instrumentation, especially the airborne instrumentation, and I'll end that lecture with a real quick overview of magnetotellurics.